Well, dear friends, in the last lecture we have developed the concept of hybridization, SP2 and SP3. We have studied relative features of SP2, SP and SP3 hybrid orbital and few examples related to the SP. Now see few examples related to the SP2. Suppose that we have BF3 molecule. So BF3 molecule, central atom is boron. So see electronic configuration 1s2, 2s2 and 2px1 or 2py1, 2pz1. You can write 2px1, 2py0, 2pz0. So this is the ground state electronic configuration of this atom, right? Now see if this ground state configuration of boron is involved in hybridization, then how many possibilities are there? There are so many possibilities that it may be sp hybridized, it may be sp2, it may be sp3, because there is no restriction of the presence of this 2 electrons or 1 electron or no electron in hybridization, right? But what facts are suggesting here that this ground state is of this molecule. So what is important, that theoretically we cannot say that okay, this hybridization is there until or unless some experimental proof we do not have for the molecule, right? So on the basis of experimental facts what we have for a given molecule, and then we try to apply our concept, right? So here in BF3 molecule there is no lone pair of electron over the boron atom as we know the experimentally. Then we say okay, this 2s and orbit electron will promote into this before hybridization, because in hybridization there is no change in the multiplicity. So before hybridization whatsoever the electronic transition that will takes place, right? So in the excitation 1s2, 2s1, 2px1, 2py1 and 2pz0. Now this 2s, 2s, this 2s and this, right? They mixed. This is the energy. So 2s, 2px and 2py, they mixed with each other. This is unhybridized here, right? So these orbitals mixed together, mixing here, and now you get three sp2, sp2, sp2 and sp2, and each have one electron, each have one electron, right? Or you can write this in this way also. After mixing you will get sp2 1, sp2 2, oh sorry, sp2 1 and sp2 1, means 3 sp2 hybrid orbitals all have same energy, same size, same shape, and all have one electron. So this is and what is the orientation as per the hybridization concept? These hybrid orbitals are oriented at 120 degree from each other. 120 degree from each other. So each sp2 hybrid orbital is, this is one sp2, one electron is here, this is another sp2, and this is third sp2, 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 right? This type of geometry, what is the geometry of this hybridization? So geometry is trigonal plan. Sometimes simply we say plan, right? 120 degree bond angle from each other. So this is the hybridization in boron in Vsepr. What about this orbital? This p orbital, pz orbital, or anyone you can say px, py, whatever. This is left unhybridized with boron, and when it is required, this may be the part of hybridization, or this may form the pi bond with the adjacent atom, because this is atomic orbital and this is unhybridized here, right? So what is the future of this remaining atomic orbital? This may be in some other molecule related to the BF3. This may change, may involve the hybridization. Like I will give you the example for that as well. First, we have to see this formation of this. Now, what about F? What is the configuration of F? So 1s2, 2s2, 2px2, 2py2, and 2pz1. So this 2pz1, this will overlap with three fluorine atoms we have. So with all three and forms sigma bond. So how this can be represented? This can be represented like this. This is sp2 orientation, and now p atomic orbital of fluorine. Here fluorine, so here 1 and 1 electrons overlap. Here this will overlap, and here this will overlap. So which type of overlapping is this? This is PZ, so PZ, and this is also PZ, this is also PZ. So the type of overlapping is here 3 sp2 and PZ overlapping. So what is the nature of bond? Sigma bond. So how many sigma bonds we have here? 3 sigma bonds. Is there any pi bond? No. No pi bond. No pi bond. Any other feature? No lone pair on boron. But see, this will appear in the form of lone pair, because this is the part of valence shell, So three lone pairs are on each fluorine. So 1, 2, 3, 3 3s are 9. Total 9 lone pair of electrons are on the molecule. On the molecule means overall on the whole molecule, total 9 lone pair of electrons are there. Is how many electrons are there in the valence shell of boron? So only 6 electrons are there. 6 electrons in the valence shell of boron. Boron means it is electron deficient. Electron deficient, right? So this molecule is electron deficient. How this can be represented? Now see, if you are representing BF3 molecule like this, BF3. So this is a incorrect representation of BF3 molecule, because now you are knowing that there is a bond angle between these bonds is 120 degree, right? So now you have to develop the habit and make it practice, that you have to uh, draw the Lewis structure of boron like this and approximate, structure that had the bond angle 120 degree from each other. This is a symmetrical structure, and if it is symmetrical, then there is no polarity on the molecule. If it is symmetrical, so obviously this molecule is non-polar. Although it has polar bond, there is a difference in the electronegativity, but it has polar bonds, but whole molecule is non-polar because molecule is symmetrical. I will discuss the concept of polarity in somewhere in the same chapter, but this is one concept. If any molecule is symmetrical, then you can say, okay, the molecule is what? Non-polar. This is the direct evidence. So this molecule is electron deficient. It has 3 sigma bonds, no pi bonds. One p atomic orbital is unoccupied, left in boron. This also the important feature. One p atomic orbital is left unoccupied, left unoccupied in boron. Right? So in BF3 molecule, there is one atomic orbital, which is left unoccupied. Okay. Now see other molecules of similar kind, like suppose that if you have SO2, SO3 and CO3 minus minus, in all, see, this is sulfur central atom, here carbon is the central atom. Similarly, similar molecule BCl3 and etc. all have sp2 hybridized. sp2 hybridization. sp2 hybridization, right? So now I am taking here one molecule, this sulfur trioxide, and I am explaining this, the formation of sulfur trioxide, and for rest of the molecule it is homework for you, right? So this is homework all of you should draw properly everything, whatsoever feature you can write. It is not necessary that this only feature in every molecule what I have listed here. See, molecule to molecule features are added or I mean deleted. So you have to write whatsoever possible for you, that you should write for every molecule. See, once you do this working here in class 11th, you have enough time to do working on the molecules. I mean, believe me, if you are able to do some, I mean, 10 to 20 molecules like that, you becomes, uh, you can say, master of this bond, right? And things will be visualized to you. See, sulfur trioxide, I am taking sulfur trioxide. So many times, I mean, students are confused in the structure of this sulfur trioxide. So I'm taking this sulfur trioxide, sulfur, electronic configuration, 1s2, 2s2, 2p6, 3s2, 3px2, 3py1, 3pz1. So 6, 4, 10, 10, and 15, 16. Okay. And 3d0, 3d0. So this is the I mean ground state electronic configuration. But this electronic configuration, you cannot explain the formation of this sulfur trioxide molecule, right, in this electronic configuration. You have to see, this is the valence shell. This is the valence shell. Right. So the orbitals of this valence shell are involved here. Right. The orbitals of this valence shell are involved here. See, this is very, I mean, you can say time taking, I mean, explanation of this molecule, but see carefully and we will see here thoroughly this molecule. Right. Now, this, I mean, electronic configuration will excite. So now I am not writing here. I can write here helium, neon, neon, right? And they see one electron from this 3p will move to the, I mean, 3d. One, not one, two electrons from 3p will move to the 3d, and one of 3s to 3. So the following transition will take place here between 3p and 3d transition before hybridization, and 3s3p means one electron of 3s is goes to 3p, and from here 2 electrons will go to the 3d. So total here we want all unpaired electrons and total number of orbitals involved in this bonding of sulfur trioxide molecule: 1, 2, 3, 4, 5, 6. Total 6 orbitals must be involved, right? So the electronic configuration is like this: 3s1, 3px1, 3py1, 3pz1, 3dxy1, 3p/yz1, right? So this is the order of energy, right? This is the order of energy. And now mixing will take place. Mixing of atomic orbitals. So until or unless you are not able to identify what I mean configuration is there in the molecule, you cannot I mean explain the what is the hybridization and what is the bonding in any molecule. So in sulfur trioxide, initially I am giving you, okay, this sulfur trioxide is sp2, then you have to make. After completion of this concept, I will give you some formula so that you are able to calculate the hybridization. Then after considering hybridization, then you explain the formation of the molecule, right? You know, many people are saying that, okay, from hybridization we are predicting the geometry of the molecule. This is the actually wrong concept. It is prevalent in the society, or you can say between teachers and students, right? There is no way. You know, sulfur trioxide is a planar molecule. This is the experimental evidence. This is a planar molecule. This is the experimental evidence. And now we are going to fit our theory to this fact. Suppose that some unknown molecule is given to you, you cannot predict the structure of hybridization in that molecule if this is unknown. Okay, we are trying to do some reference examples. After that, I will give you some formula, some theoretical formula, so that you can calculate. But the concept is not like this. Concept is, first we determine the geometry of the molecule, structure of molecule. We have experimental techniques to determine the structure. We do not have the technique to determine hybridization, right? We are doing this on the basis of the structure. So the fact is here that sulfur trioxide is planar. So I am doing this work, this excitation and de-excitation, on the basis of the fact that sulfur trioxide is planar. I am not doing this myself, that I am telling that this electronic configuration should be there. No, not like that. I have certain experimental evidences in which this is one of the, you can say, most efficient or most important theoretical, experimental evidence that a sulfur trioxide molecule is SO3 is planar. Now I am trying to justify this planar molecule by this hybridization. Okay, so all of you should I will follow the concept in the proper order. When I will discuss this, some reference molecules, some known molecules and hybridization in those molecules, after that I will give you some formula so that you can use. But I am not taking that guarantee that your formula will always give you the correct result. Some exceptions may be there, right? So the mixing of so this is planar. So I am considering only sp2 hybridization, means 1s and 2p orbitals to be mixed. Only this mixing will take place here. And this pz, dxy and dyz, they were left unhybridized. So here you will get sp2 1, sp2 1, sp2 1 means 3 sp2, 120 degree from each other, and this 3pz 1, 3dxy y1 and 3d 3dyz1. So these three atomic orbitals, these are atomic orbitals and these are hybrid orbitals. So now total how many orbitals you have at sulfur? Three, I mean this hybrid orbital and three atomic orbital. Total 6 orbitals are present around the sulfur. And now see how many orbitals before mixing this sulfur had. So 1, 2, 3, 4, 5, 6. So before mixing, sulfur also had 6 orbitals, but all 6 are atomic. Now after this, it has 6, 3 hybrid and 3 atomic. Okay. Now I'm not going to draw these orbitals here. I am directly going, because all these orbitals are the sigma. So that otherwise drawing of 6 orbitals around the center, that will very cumbersome structure. So here I am taking sulfur. These 3 bonds will be at 120 degree from this. (120 degree) and 3 oxygen atoms are there. Now see, this is the skeleton of this. This will determine the geometry. The orientation of these, atomic orbitals. See, orientation of these orbitals will not determine the geometry of the molecule. The orientation of these 3 will determine the geometry. Okay. The orientation of these hybrid orbitals will determine. So these 3 hybrid orbitals are at 120 degree. This is the geometry of the molecule. So this is planar, right? So this is 120 degree, right? Now see, do some working on oxygen. See, oxygen configuration is 1s2, 2s2, 2px2, 2py1, 2pz1, right? And we have 3 oxygen atoms, and these 2 atomic orbitals will overlap. So I am considering here that this if I can write here, so to show you, I'm writing here, this is sulfur, because this is very wait, sulfur have sp2, sp2, sp2 and 3pz 1, 1, 1, 1 here also, 3dxy and 3dyz. So first you can see that which atomic orbital of oxygen will form a pi bond with this. See, pz of one oxygen atom. See, oxygen atom has two atomic orbitals. So one of each will overlap with this sp2. So we can say that y, z, z, x. So here I can take x instead of x, y. I can take here, or because this should be, justified. 2p y and z. Okay, y and z, yes. So y, z, y, z. Okay, x2. So one oxygen atom, 3py, 3pz. Okay, 3pz, 2pz, pz, pz, and pz. They will overlap with these hybrid orbitals. Suppose they will form sigma. Here this will overlap to form sigma bond. This will overlap to form sigma bond. Now one oxygen atom, pz. So we can say one atom py overlap here. Py is overlap with this and form sigma bond, and pz is left here to form the sigma. And here uh, py and py. So see dxy. See dxy. Suppose that we have this is x, this is y, and suppose that this py. Now see, we can take here. So for your better visualization, we can take here px of one oxygen. So if we see here, this is x. So this is molecular axis. So plus minus. So this will form a d pi p pi overlapping. So here pi bond will form d pi p pi. Similarly, yz and y, they also forms the pi bond. So here pi bond, here pi bond, and this overlapping also produce pi bond. See, three pi bonds were produced, and here three sigma bonds. This is sigma, this is sigma, and this is sigma. So I have shown here these three sigma bonds, and now see pz, one oxygen atom. This has, suppose that this is x axis. So we cannot show here axis because this is what, okay. This is PZ, PZ. So sulfur also have one PZ, one electron both. So they will overlap and form a pi. So this is one oxygen atom which 3 pz and 2 pz. This is 2 pz, this is 3 pz. See, this is 2 pz and this is 3 pz. They will form the pi. Now this sulfur has dxy and one oxygen has px. So this sulfur dxy. So I am showing this separately so that you can easily understood, right? Otherwise, this will very, I mean, cumbersome. So dxy, suppose that this is x-axis, this is y-axis, this is x-axis. So dxy, right? And this oxygen have this X. So this oxygen have X. So see, this is positive, this is negative, and this is positive, positive, negative, negative. So this will form a pi bond. So here px and dxy, px of oxygen and dxy of what, this sulfur. Similarly dyz and py. So similarly I mean this sulfur will form another pi bond with D, but I mean not required to show here. Now you can understood with this I mean representation, this representation. This is sigma, this is sigma, this is sigma, this is pi, this is pi, this is pi. It is very difficult for us to, I mean, draw all those, I mean, orbitals here. But actually they will overlap in that manner. So now I am showing here sulfur double bond this oxygen and double bond this oxygen and double bond this oxygen. And each oxygen has two lone pair like this, like this. Now see here in this sulfur trioxide molecule, three pi bonds are there, and all three pi bonds have same feature. The answer is no. One pi bond is formed by the PZ overlapping, means P pi bond, and two pi bonds are P pi D pi, right? So this molecule has three sigma bonds, and three pi bonds, in which two pi bonds are D pi, P pi, and one pi bond is p pi p pi, right? And how many lone pairs? 2 to 4 to 6. 6 lone pairs on overall molecule. And sulfur atom has no lone pair. How many electrons in the valence shell of sulfur? 12. 2 to 4 to 6. So total 12 electrons means 6 bond pairs. 6 bond pairs around sulfur atom, right? Around sulfur atom. So this is electron rich molecule. This is electron rich. See, all pi bonds have same length. The answer is no. This these two pi bonds, suppose that this is X and this is Y pi bond. So X is larger than Y. Why? Because this is d pi p pi, this is p pi p pi, right? So d orbital is larger than p, so obviously the size will be different. So see, and different bond energy also. Different bond energy also. Which one is weaker? Obviously d pi p pi is weaker. So in this way, if you are able to visualize, then definitely, there is no problem in chemistry, right? So this is a very, complicated molecule, sulfur trioxide molecule. It is very difficult to explain. This X, Y, Z, bonding pattern in this sulfur trioxide. So all of you should try show the formation of sulfur dioxide, carbonate ion, and PCl3 is very simple. So one feature is common for all, that all are planar, right? So in SO2, one lone pair should be there in here, right? Only one excitation will take place, and in carbonate, already carbon is always in excited state. So do try to explain the formation of these two molecules as a homework, right? Now I am taking next hybridization, that is sp3. sp3 hybridization. Now see, in sp3 hybridization, uh, what is the geometry of the molecule? Geometry is tetrahedra. Bond angle is 109 degree. 109 degree 28 minutes, or 109.5 degree, right? So this is the characteristic feature. So if you see example methane, this carbon sp3 hybridized, uh, uh, ammonia, nitrogen is sp3 hybridized, H2O, oxygen is sp3 hybridized, NH4 plus, nitrogen is sp3 hybridized, and BF4 minus, boron is sp3 hybridized, right? Uh, SO4 2 minus sulfur is sp3 hybridized. So etc. So all these in all these molecules the central atom is sp3 hybridized. So all have tetrahedral geometry and all have this all may have the bond angle 109 degree 28 minute, right? Some of them have a bond angle equal to this and some of them have not bond angle equal to the 109 degree 28 minute, right? So see this if we consider this methane, so carbon has configuration 1s2, 2s1, 2px1, 2py1, 2pz1, 2px1, 2py1, 2pz1. This is the excited state electronic configuration. This is the energy, and after mixing, they will produce sp3 1, sp3 1, sp3 1, and sp3 1. 4 sp3 hybrid orbitals each have one electron. What is the orientation? 109 degree 28 minute tetrahedra. Right, each have one electron, and hydrogen will overlap, which is a non-directional, so no problem. So here two electrons. So which type of overlapping is this? This is basically sp3s overlapping, and all four bond lengths are equal. Everything is equal here. In methane molecule, all bond angles are equal. So you can explain the formation of this molecule with the help of hybridization. What X-ray suggested, that you have justified with the help of this sp3 hybridization, right? So this is sp3 hybridization. All S and 3p are mixed and produces four equivalent hybrid orbitals, right? So this is all about methane molecule. Now ammonia, water, and other molecules. This I will explain the formation of ammonia and water molecule. All of you, if want, you can try these two as a homework, right? Ammonium and BF4 you can try as a homework, right? And I will explain the formation of ammonia and water molecule with a special reference, right? Okay. Now see ammonia molecule. So in ammonia, the experimental bond angle is 107.5, which is closer to 109 degree 109.5. Thus we can say that nitrogen in ammonia, nitrogen atom in ammonia, is sp3 hybridized. Right. See, this 107.5, this is closer to 109.5, because this 109.5, this is the standard bond angle for sp3. So you can say, we can say that, okay, this nitrogen is sp3 hybridized, because it cannot be sp2, because sp2 is 120 degree, and cannot be sp because that is 180 degree. So this is the way to explain the hybridization. So if bond angle is not exactly equal to the standard bond angle, it is nearer to that. So you can say, okay, this atom may have this hybridization, right? So if we consider sp3 hybridization in nitrogen, so see what is the electronic configuration: 1s2, 2s2, 2px1, 2py1, and 2p 2pz1, right? So they mixed with each other. Right? Mixing will takes place. All four will mix. And produces sp3. 2 means one sp3 has 2 electrons, then sp3 1, sp3 1, and sp3 1, right? So you have 4 sp3 hybrid orbitals, in which one hybrid orbital has 2 electrons and 3 hybrid orbitals have 1 electron. Now, see, dissymmetry is there. See, some degree of unsymmetry, dissymmetry is there or not. See here 2 electrons, here 1 electron. So obviously some extent of dissymmetry now will come here in this molecule. So and that reflects here in the bond angle, right? Now see the nitrogen, you can see like this: 1 sp3, second sp3, and one have 2 electrons, and rest 3 have 1 electron, and this hydrogen will have 1 s1. So this hydrogen will overlap. Hydrogen will overlap. So you will get what? This is, normal orientation is 109 degree 28 minute, but due to some, dissymmetry in the, orbitals, we have distortion, and we get lone pair here. So the bond angle here, H and H bond angle is 107.5, right? So what is the geometry of this molecule? So geometry, see, there is a difference between geometry. Geometry is, regular. So geometry, here you have to say I will explain the geometry with the help of hybridization. So geometry is here tetrahedra, but now the shape you can say distorted tetrahedra, distorted tetrahedra, or you can say this shape is called pyramidal shape or pyramidal shape, right? Because the bond angle is not exactly 109 degree 28 minutes, so the geometry is distorted. I mean shape is distorted tetrahedra, but geometry it is at any moment of time when geometry is asked, so geometry you have to see only hybridization. See the hybridization, what is hybridization, then you have to say okay geometry is this. But shape is the overall actual. So basically shape is the actual and this is theoretical, right? This is actual, right? So how to theoretically we can explain this decrease in bond angle in ammonia? That requires another theory of bonding, and that is explaining Vsepr model, valence shell electron pair repulsion theory, right? So all of you should be prepared for the next theory, that is known as Vsepr theory. So here we can put a note that if central atom has lone pair of electron or electrons, then the geometry of molecule is not regular, shape of molecule is not regular, right? And there is some extent of distortion due to different types of repulsions present in the molecule, right? So this is the explanation of the formation of ammonia. So similar case with water also. In water there are two lone pairs, so the water has also not the same shape and geometry had not the are not the same. They are different, right? So one by one we will now see water molecule. Water molecule in water, uh, the bond angle HOH bond angle is 104.5 degree experimentally. Now, what kind of hybridization you can predict in the oxygen here? What? There is no d orbital in oxygen, only s and p orbitals are there, so only sp, sp2 or sp3, because this is the maximum 3 hybridizations are possible, and this bond angle is closer to 109 degree. So what hybridization you can say? Only sp3. So this bond angle is closer to or close to 109.5 standard sp3. Thus oxygen atom in H2O is sp3, because we cannot say sp2.5, although some index hybridization is there in some cases where when the property is not very close, then you can say okay some p character will increase or some p character will decrease, accordingly the molecule will adjust. But first time you are studying this, so you interpret in this way. Now see the oxygen. So oxygen 1s2 2s2 2p x2 2p y2 2p z1. Now see, this is the energy, and they mixed mixed, all these orbitals are mixed, and after mixing it will produce sp3 with 2 electron, one sp3 with 2 electron, other sp3 is also with 2 electron, and 2 sp3 are with 1 and 1 electron, right? 2 2 1 1 1 1, right? So now 4 sp3 hybrid orbitals are there, like this, and all are equivalent, and all are adjacent to each other. Don't try to put one lone pair here and one lone pair here and say, okay, this is the far apart. Don't say like that. All the lobes are equivalent, all have equal bond angle from each other, so there is no lobe is anti to each other. Try to understand, this is 3D geometry, right? This is 3D. In the next lecture I will show you the model, this structure with the model, right? So this is 109 degree 28 minutes. So don't say that one lone pair is here and other lone pair is here, so they are anti to each other, so to minimize the repulsion. Some people are explaining like this, right? But they were wrong. See, all the lobes are some adjacent to each other, so you can put your lone pair anywhere. Don't no problem. And 2 electrons are like this, and 2 hydrogen will overlap here and form a bond, right? So O is here, one hydrogen is here, one hydrogen is here, and one lone pair is here, and one lone pair is here, right? And what is the bond angle here? The bond angle is 104.5. So what is the geometry of this molecule? So geometry you have to explain with the help of hybridization. So tetrahedra, and shape you can say distorted tetrahedra, or we can say V shape, right? So once the lone pair will come at the central atom, geometry is not regular, it will adopt a new shape, right? And in that case, geometry and shape are not the same, right? So this is the formation of what water molecule. 2 sigma bonds are there, sp3s overlapping is there. Now you can write all these features. 2 sigma bond formed by sp3 and s overlapping, 2 lone pairs, no pi bond around the oxygen, right? So all these features now you can write.